right, this should be recording. Hello, everyone. I am making some recordings to help you guys prepare for test 3. This is already the part 1, or assuming there's 2 parts, part 1 of the test 3 review session. I'm leaving town next week, so I will be gone anytime after test 3. So I'll just be grading things and answering emails and group me's, but I probably will not be able to have office hours because, again, I'll be out of town. You know how summer is. But without further ado, let's go ahead and do what we can with the limited time we have left together, because your final's already next Saturday. Alrighty, let me go ahead and share my screen. Give me 1 sec. There we go. You guys should be able to see my screen. And just a heads up, make sure that we're using the fall 2018 review session packet, not the 2019. The 2018 I made prior notes for, so this is going to be the most helpful one. You can take a crack at the 2019 one, but this is the one I'll be using for this review session. So the first thing we come across is resonance structures, and this is relatively easy concept once you get the hang of it, especially for this test. And I see it as, well, once you get it, free points on a test, which is what we like to see. On the problems, you guys did pretty well. Hopefully you guys saw the video I posted. But even so, the biggest issue I found was people not circling the most stable resonance structure. And don't forget, whatever original structure you have, that's also eligible for the most stable, because as it's written, the way it's written could very well be the most stable form. So don't forget to consider that. Let's go ahead and think back on our moves. Okay, so the easiest move, most common move we have is a door hinge, where if we have a sp2 carbon, sp2 carbon, the positive charge, and these are also sp2, we can shift this alkene over there and just basically flip it over and conjugate it over here like this. Because in real life, the resonance structure would look something like this, where it's a mix of both. That's the hybrid. All right. Additionally, we can also donate or take away electrons, but that's kind of a weird thing to look at. If you had something like this, the oxygen can donate a lone pair and make that into a carbonyl, something that looks like this, where there's no formal charges. And conversely, it can also go back. Don't forget, wherever we create a charge, the countercharge has to also be created, because the net charge for all the resonance structures have to be the same. So if we take away charge away from this and add charge back to that oxygen, well, there's a deficit of that positive charge and an excess in that oxygen. Just some helpful notes, but it's a lot better to see it in person, or not in person, but on paper. Let's go ahead and work with this first one. So we can go ahead and do a door hinge move, because we have, all right, sp2, 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 and sp2. Don't forget, sp3s don't play anything at all with resonance structures, or at least when we're shifting them around, because this has hydrogens on it. There cannot be any bonds with that carbon with any other carbon, because if you do, you're going to overload it with 5 electron groups, or specifically exceed the octet. So make sure you keep an eye out for that. sp3 carbons are not what we want. Anyway, let's go ahead and do what we were originally doing and hinge that over there. If we did, our compound would look something like this, where we moved, again, this alkene over here like a door hinge, and then this positive charge trades places. Now we have a compound that looks like this. We can do it again with this, because again, those sp2 carbons are right next to each other, close proximity. We can do that again, so that it looks something like this, right? Now, when we're looking at the most stable, well, first off, the first rule for the most stable compound is the most number of bonds, specifically the most number of pi bonds, because the more bonds there are in a certain resonance form, the more it contributes to the resonance structure, because bonds are a lot more stable form for electrons, so they would prefer that. Another big thing to look at is the least amount of formal charges. This is a Gen Chem concept where the most common resin structure is the one with the most resin or the most formal charges that are like zero or really close to zero. So you're less likely to see a compound with a positive +2 and a -1 formal charge if another resin structure has like, I don't know, +1 and a 0 formal charges. But that's beyond the point. The next thing is looking at the types of atoms you have. Charges like to be on certain atoms, electronegative or electropositive. And for here, all of our formal charge holding atoms are carbon. So we have to look at substituent pattern. So they're all secondary. None of them are tertiary, which is the ideal for a carbocation, and none of them can be ruled out because they're primary. So if they're all secondary, they're all equally stable. With that all together, let's go ahead and work on this one. We can door hinge that over there. Positive charge here, right there. And we have another carbon right here that we can shift that over with. Right here. And remember, we cannot cross over carbons because this one already has 2 hydrogens on it. It's sp3, so it cannot be part of that conjugation system. Now, out of these, which one is the most stable? Well, all of the atoms are carbon, but before we look at that, all of them have 3 pi bonds, so we can't rule out anything just yet. And if they're all carbon, let's look at their pattern. They have a primary, tertiary, secondary. Tertiary is the ideal for a carbocation, so that's the most stable. Let's look at this. All right, well, we have a compound that, well, first off, we can do door hinge over here. That's the first move we should do, because if we're looking at the oxygen, it can't donate electrons anywhere because it's already sp2, and that's just a methyl group. It can't hold any more electrons. So let's go ahead and just move it over there and just move that electron deficiency over here. All right, now we can donate this over. Positive charge, CH3. Now looking at these, which one is the most stable? Well, first off, we have to look at the most number of bonds. That's pretty easy, this one. Even though it might seem counterintuitive, well, we have a formal charge on an electronegative atom like oxygen. That's still better than having a positive formal charge on something like carbon. And our electron system is better suited for those pi bonds. So that's a lot more favorable. Now let's look at this. All right, well, this is sp3, so we can't move anything that way, but we can door hinge that over there. And H2. Now again, look, we can donate electrons here. Nope. H2. Now, which of those 3 is the most stable? Well, NH2 has the most number of bonds, so that's the most stable. And something that I want to point out is you have to make sure that all the formal charges balance out in every single structure. So the net charge for this one is +1. So the net charge for every other resin structure has to still be +1. This is +1 still, and this is also +1. If it's different, then something is wrong with your resin structure. And this is always the case. See, +1, and all of these are +1. Now let's look at this. We have a net charge of +0. Let's keep that in mind. All right, well, what can we do here? We can't door hinge any of these alkenes over here quite yet, because if we did over here, this would be overloaded because that's already an sp2 carbon. This is an sp3 carbon, so we can't take away any of those hydrogens. What can we do? Well, we can create charges by moving electrons onto that oxygen. All right. If we move the electrons over here, we would have a negative charge here. And wherever you have a negative charge, you create a positive charge. Don't forget to keep moving it one step at a time, because every resonance structure should be noted. All right. So this right here is a very bad resonance structure because, well, look at this. You have a positive negative charge that are pretty close to each other. That's not what we want, but it's still a valid resonance structure. So we still want to write it down. It's kind of like the point of this portion of the test. Look at the net charge. That's positive and negative one. That cancels out to 0. Let's move this around. Let's door hinge that over there. Right here. And there's this portion of the review session or the review packet kind of skipped another valid resonance structure where we door hinge over here. Something like this. And another mistake is, I think the answer key did not put that positive charge there. There is supposed to be positive charge there. Because again, if you look at both of these different structures, the positive and the negative cancel out, the net charge is 0. All right. Now let's move on to, actually, let's skip that one for last. This one, I don't think lecture quite hit on just yet. I think they did, but not very much. I'm going to focus more on the more recent stuff. The Diels-Alder reaction is a super important reaction. In semester 2 lab, some groups might tackle it, and I'm pretty sure he said it shows up in the MCAT. So this is a very important reaction for many of you. The big thing to note about the Diels-Alder is this summary reaction right here. You need a cis diene and then a dienophile. Dienophile is pretty common. It's just an alkene. It usually is an alkene, but the this diene right here has to be cis to each other because it forms a cyclic structure or pericyclic structure. So they need to be right next to each other. And don't forget, this bond right here can freely rotate because that's a sigma bond. So this portion can rotate however it can. So if you have a diene that's like this, that's a valid diene because it can very well be rearranged into something like this. Like that. Or I just rotated this bottom portion around. An example of an invalid diene would be something like this. If a diene was limited by a cyclic structure, we can't rotate this around because it's part of a cycle. So this is locked in a trans diene conformation. So if we added it to a dienophile, we get no reaction. All right, with that in the back of our head, let's go ahead and just move on out. Right here, just basically you open these up to form bonds. I don't know how else to write it out. There's a lot going on, but it's concerted. It's one step. If you have any questions, I think there's a crash course video that goes pretty in depth in this, and it's pretty cool. But in exchange for a ring structure, you basically subtract 2 double bonds from your original 3. So there should be 1 double bond left. So you can't forget that because that double bond derives from one of these flipping on down. Okay. So this is maleic anhydride. This structure, I don't really like it the way it is. So I'm just going to redraw it. It's better to visualize our diene. So we have our 2 cis diene groups and we have our 2 methyl groups. All right, we're going to add it on this side. So what was our diene system now flip out? No, flip out that way, flip out that way. This flips out this way. And they form these symmetric bonds here. If we were to redraw it, it looks something like this. Something like that. All right, again, we have cis-diene, so that passes the test. And we just have a simple alkene that can open it up, right? And a thing to note, it attacks one way. So our diene system are tagging these carbons in one direction. So our the way it's adding would be into the page facing that way. It's kind of hard to draw in 2D. One of the drawbacks of having an online class, but that's beyond the point. The point is this is cis. So whatever groups you have, whatever your alkene you have, if one of the regions are cis, your products have to retain that cis structure. So if you were to draw it out, conjugate over here, this would imaginary opening right here. It looks something like this. Yeah. CH3, because remember they're cis to each other, and then hydrogens would just remain on that end. Perfect. Again, right here, that way, open up that way, open up that way. So I just basically see this door hinge it open, something like that. You get something like this. Like that. Perfect. Now we get into asymmetrical deals all the reactions. This is pretty tricky because we get two products. One where it just adds normally straight across, and one product where this just inverts itself around and adds upside down. Which one is the major product? Or is there a major product? Well, the answer is yes. And for this, we have to look at charges. So for electron withdrawing groups or donating groups, I just draw partial charges to line them up. What I mean by that is, well, it makes a lot more sense if we draw that. Oxygens are partially negative. It's very electronegative. So they pull electron density toward themselves. And it kind of alternates like a zigzag. All right, if this is partially negative, this is partially positive. If this is partially positive, this has to be partially negative. You guys feel? And this has to be partially positive. And we use the same logic over here, negative, partially positive, partially negative, partially positive, partially negative. And what we want is to line them up. We want negative to partially align with partially positive to align with partially negative, right? This way, these are already lined up the way we want. We'll get a major product of this. Secondly, if we get a pericyclic compound, if our diene is cyclic already, this lip has to fold up because these would attack, well, these carbons right here to form a structure like this. This right here is the lip of that pentadiene, cyclopentadiene. And determining which one's the major product, well, it's always pretty much going to be the end of product, where we have whatever group we have facing away. If it's symmetrical, both will be the same, but the point of this is showing which one we want, endo or exo, and this one would be the endo, because we want the steric sides to face away from our pericyclic compound, because a lot of things are going on over here. We want another big group to just stay away from it, because sterically, it's not going to hinder it as much. As you see here in the exo product, it's kind of up in the business, so we don't really want that. And for memorizing which one's exo, which one's endo, straight up, you just have to memorize it. Endo faces away or into it. Exo is facing outside of the compound. All right. Now we get into the meat of test 3, and that's substitution and elimination reactions. This is one of the topics that gives organic chemistry a reputation. This is a tough subject to wrap your head around and needs a lot of practice. One of the upsides of having it in person, but one of the downsides of having it online, you have to learn this stuff pretty quickly. Thankfully, we have charts. So the first thing to note are our reagents, weak bases, strong bases, and having no complex reagent, or our nucleophile is just our solvent. Something that you'll see for strong bases are these negative charges. And the way we denote that is just having it written as Na, or having it paired with sodium, a counterion. Because remember, sodium usually has a positive charge. So they're ionic bonds with something like this. CH3, 3. So if we were to draw the reaction, it would be written out like this. Whoops. All right. As you can see, these are conjugates of each other. Because remember, in an aqueous solution, these dissociate. So all you would have left would be that ion. So if you have something with sodium at the beginning, right here, it's synonymous with just taking away that nitrogen and putting that minus charge there. It can better show us what nucleophile we're dealing with. Thankfully for our substitution reactions, weak bases and strong bases are pretty mutually exclusive. Weak bases can only do substitution reactions only. They're not strong enough to force an elimination. So for here, methyl group, SN2, easy. For primary leaving group, SN2, easy. This one, SN2, really easy. For tertiary, there's no reaction because there's too much steric hindrance in order for whatever weak base you have to get in there. Strong bases is where it kind of throws things off. So for methyl group, that's only a CH3. Right? That R, let's just say it's like ER. Don't forget, strong bases are usually correlated with E2 reactions. However, there are some cases where that's, well, not the case. Methyl groups are one of those cases because there's no bond that can be formed from that methyl group. There's no beta carbons. There's only one carbon that's already alpha.
Yeah. You always do somewhere nice.
Thank you. See ya. Sorry about that. This is SN2. You can only have SN2. Right? Now for primary, this is where it gets a little weird. For a small strong base, we get SN2. For large strong base, we get E2. For a small strong base here, we get E2, but Zaitsev product. This one we get large strong base, E2, Hoffman product. And at the time of recording this, I haven't had office hours where we talked about this quite yet, because I'm recording this on Thursday, June 23rd. And in all honesty, I'm probably going to make this point tomorrow. We can't study this as much as you can, but in all honesty, this chart is pretty much memorization. There's no work around it. So if you're having trouble memorizing it, I mean, you can probably find neat tricks, but you just have to memorize the pattern and visualize it out. That's all I have to say. And same goes for tertiary. E2, Zaitsev. E2, Hoffman. However, this is the real money maker when your nucleophile equals a solvent. So that's when your arrow just has H2O, like, and then some kind of temperature. Let's say like it's, I'll just leave it as pound. Or let's do CH3OH. There's only one reactant. That means your nucleophile equals solvent, and that's usually indicative of SN1 and E1. All else will be SN2 and E2. All right. And the thing is, it only really happens with tertiary. E1 and SN1 only happen with tertiary carbons. So you can already just no reaction, most of these. And then you can just do SN1 or E1. Tertiary. For SN1 and E1, SN1 is low temperatures, so like 0 degrees Celsius, and then E1 would be high temperatures like 50 to 100 degrees Celsius. This is a pretty handy thing to look at. I guess just the general trends, when you're looking at strong bases, large strong bases usually give you, or they will give you Hoffman products. And it kind of depends on the compound, because something you have to remember is E2, you have to have an anti-periplanar hydrogen. Sometimes there's only one anti-periplanar hydrogen you can look at, so it has to go that way. There are certain rules that basically tunnel certain conclusions. Another thing is like if you have a benzylic or allylic leaving group, sometimes there's only one direction to go, and that's Hoffman. For example, let's take a benzylic. Let me draw out the double bond so it's easy to visualize. Something like this, Br. All right. Well, we know that for secondary, right here, large strong bases usually mean Hoffman, and small strong bases is Zaitsev. Well, this is secondary. Which one's Hoffman? Which one's Zaitsev? If we react it with a large strong base, like NaOC CH3, 3, which way can it go? Well, the thing is, you cannot go that way, because that's already sp2. That's an sp2 carbon. There's only one way to go. That's right here. Look at the way look at it. This carbon only has already fills up that octet. There's double bond here, single bond here. There's no hydrogens. Well, this one has plenty of hydrogens that are anti-periplanar. So there's only one way it can go. That's that way. That's an example of a hyper-specific situation, but I think I posted a chart already about that, and we'll probably talk about it more tomorrow. The other thing is small strong bases are always pretty much correlated with Zaitsev. And you might hear me reference this later, but the example I just showed, that's where conjugation takes priority over Zaitsev. Let me go over here. Where's my TA copy? There it is. Let's fill in this. Okay, so this is a portion where, okay, the chart that he gave us during class today, Thursday, let's just fill it out, okay? So weak bases can only react with methyl, primary, or secondary. And they always give SN2. So we know that this is SN2, SN2, SN2. While tertiary, there's no reaction because it can't get in there. The same goes for our solvents equaling our nucleophiles. So we can go ahead and write no reaction for these. And then again, it can only react with tertiary, so it gets a check mark. Low temperatures, like 0 degrees, we get SN1. High temperatures, like 60 degrees Celsius, we get E1. All right. Now let's look at our strong bases. Well, if it's methyl group, there's no double bond that can be formed, so it can only do substitution. And look at that, we only have 6 slots left. We're already mostly there. You don't have to be perfect with this. If you get something wrong, don't beat yourself up after it, because it takes a lot of practice, and 1 or 2 points is insignificant compared to like doing a mechanism or the synthesis question with this stuff. All right, yeah. So for primary, for small strong base, we get SN2. For large strong base, we get E2. And for E2, well, if it's primary like this, there's only one way you can go. There's no There's no Zaitsev-Verhoeven. So it's just E2. If you write E2Z or E2H, it will be kind of wrong because sometimes he's really specific with that and he just wants you to know, or he wants to make sure you know that there's no other option. It has to be E2. So there's no difference in what kind of Zaitsev-Verhoeven you go with. For here, small strong base, E2, Zaitsev, E2, Hoffman. Same thing over here, E2, Zaitsev, E2, Hoffman. There we go. And again, that's just straight up memorization. Right. Let's do some more practice with this. So this kind of table where you predict the reactions is pretty much what he's going to give you, where you have to use or utilize that chart that he gives you or what I give you is basically regurgitated back out to see if you know what you're doing. So when you're given something like this, I go ahead and just identify what I'm working with. So right here, we have a small strong base. We have a nucleophile equaling our solvent. That's low temperature. So you read kind of inkling, that's going to be SN1. We'll see though. There's going to be a weak base. It's going to be a large strong base. This is going to be nucleophile equaling our solvent at a high temp. Now let's go downwards. We have a methyl group. We have a tertiary, primary. We have an allylic. We have a secondary. This is not benzylic because if it was, that CL would be there. So if we were to look ahead and if we had a SN1 or E1 carbocation, that'll be right here. It cannot conjugate over here. Cannot move over that one carbon because this is sp3. So we can't cross that. So that's secondary. This again, we have tertiary. And here we have tertiary. Allylic. All right, well, I think the easiest thing we can do is the weak base because weak bases can only do SN2, and that's only with methyl, primary, and secondary. So for this one, SN2. Tertiary, there's no reaction. Primary, SN2. Primary, SN2. Secondary, SN2. And tertiary, no reaction. We already got a fifth of that done, and we just use our knowledge of weak bases. So that's at least 20%. Let's look at our nucleophiles equaling our solvents. They can only react with tertiary or allylic and benzylic compounds. So we can go ahead and write no reaction for anything that's not that. So methyl group, no reaction. Primary, no reaction. Secondary, no reaction. All right. Now let's look down here. Tertiary, perfect. With low temp, we're going to do an SN1. All right. Primary allylic. You might want to put no reaction because it's primary, but don't forget it's allylic. So that positive charge is stabilized by conjugation. So it's perfectly valid to do SN1. Your tertiary, that's going to be SN1. Another tertiary, SN1. Boom, already 40%. Now let's do the same thing with high temperature, where we're going to usually see E1. So the same deal, no reaction. No reaction for primary, no reaction. And now we just have four more. Tertiary, E1. Primary allylic, this is going to be, I think it's E1. E1. Primary allylic would actually be SN1. It would be SN1. The key is wrong here because I realize you can't make a double bond right there. It has to be allylic. And I'm pretty sure the chart that I sent out was recently verified by Dr. Berg, and I forgot there is an error on the answer sheet. It is SN1. This is E1, E1. Now we're 60% through. All right, the recording should be continuing. Sorry about that, I had to get something. Okay, did this. Now let's get to the tough ones, which is small strong base and large strong bases. Thankfully, it's just 40% of our chart. Let's go ahead and look at this. Well, if it's methyl, we can only do SN2. Thankfully, because there's no double bond to be formed. For tertiary, we have to look. All right, small strong base, we get Zaitsev, E1, Zaitsev. So we get something either here or double bond over there. It depends on which one. Is that right? E1? That's supposed to be E2. I'm so sorry. And then conversely, this is E2, Hoffman. And don't forget, for up here, we get, if we have a small strong base, if our leaving group is a bad leaving group, which is mainly going to be fluorine, then we get Hoffman. That's another really big exception that he will probably throw at you. Going back to this, all right, primary, we get over here SN2, and we get E2. Remember, there's only one direction we can go for that double bond, so it doesn't really matter. It can neither be Hoffman or Zaitsev. It's just a normal E2, and he will count it wrong if you write H or Z. It's just E2 straight up. Allylic. Well, this is primary. We have SN2 like normal. But for this one, again, only SN2, another weird exception. But if you look at it logically, there cannot be double bond formed. So whatever large strong base you have, its only option is to do an SN2. And just because it can't do it doesn't mean it'll do it well. But the fact is, he wants to make sure you know that it can happen, and it will, albeit it could be very slowly, terribly, but it can and will. Now let's get into our secondary and tertiary stuff. Now we're back in the group of things. Secondary, okay, U2, Zaitsev. Double bond will be formed here. For this one, E2, Hoffman. Double bond will be formed here. Same thing here, we have tertiary. All right, this is secondary, and these are primary. So there is a difference, E2, Zaitsev, E2, Hoffman. Now look at this. We have, look, secondary, same again, primary right here. So there's a difference between Zaitsev and Hoffman. But in actuality, no. There can only be double bonds formed between those primaries. And this is not a stereocenter. They're the same. So it doesn't really matter which way we go. This is just straight up E2. Because there cannot be double bond formed with that carbon. Right? So that's that chart finished. I think I might pause the recording here and just keep this as part one, because this stuff I'll probably tackle during office hours tomorrow. Yeah. And then the rest, if I make another recording. Let me stop my share.